All right, let's dive right into this stack of research excerpts you've given us.
Yeah.
It seems we're dealing with some pretty high-level topology here.
Right.
Specifically, almost Hermitian structures on moduli spaces of non-abelian monopoles.
And not just any moduli space, it seems.
Right.
The focus is on those spaces related to a proof of the Bogomolov-Miyakoyau inequality.
Okay.
Which, as you know, is a pretty big deal in the world of four manifolds.
Right now, I always find it helpful to start with the why before the what.
Sure.
So before we get into the nitty-gritty of these almost Hermitian structures and non-abelian monopoles,
Okay.
remind me why this inequality is so important.
Okay.
What's the impact beyond just the equation itself, which, for our listeners playing along at home, is 3C row?
Excellent point.
Yeah.
The Bogomolov-Miyakoyau inequality gives a powerful tool for understanding the relationship between certain topological invariants of four manifolds,
Okay.
specifically the Chern numbers for Euros,
Right.
by constraining these invariants. The inequality helps us classify and understand the structure of these complex four-dimensional spaces.
Right, because classifying these spaces is notoriously difficult.
Yes.
It's like they have a life of their own.
Exactly.
Compared to more well-behaved manifolds in lower dimensions.
Exact. And that's what makes this proof strategy so interesting.
Okay.
It uses these exotic objects,
Right.
non-abelian monopoles, and their moduli spaces
Right.
to tackle a fundamental problem in four-dimensional topology.
Okay, so let's unpack this proof strategy a little bit.
Okay.
The excerpts mention constructing an almost Hermitian structure on the blow-up of a four-manifold.
Right.
Now, I remember from my algebraic geometry days that blow-ups are a way of surgically modifying a space to resolve singularities.
Right.
But why blow up the four-manifold in this case? What's the advantage?
Think of it this way.
Okay.
Sometimes a problem is easier to solve in a slightly modified setting.
Okay.
Blowing up the four-manifold allows us to work with a space where the Bogomolov-Miyakoyau inequality might be easier to prove. It's like adding scaffolding to a building to make repairs.
Right.
You're not changing the fundamental structure, just making it more accessible.
That's a great analogy.
Yeah.
So we're strategically modifying the space to simplify the problem, but we eventually need to connect the result back to the original four-manifold, right?
Precisely. And that's where the power of this approach lies.
Okay.
The excerpt suggests that by constructing a particular kind of almost Hermitian structure on the blow-up,
Right.
one that's carefully chosen to interact with the non-abelian monopoles,
Okay.
we can derive the inequality on the blow-up
Right.
and then relate it back to the original manifold.
Okay, so the almost Hermitian structure is a key player in this strategy.
Yes.
Can you remind me what makes these structures so special?
Yeah.
The excerpts mention something about rotations and measuring distances and angles.
Right.
But in this abstract setting, it's hard to picture.
Imagine taking a space and equipping it with a way to rotate things by 90 degrees in a consistent way. Like having a tiny compass at every point telling you how to turn.
I see.
That's essentially what an almost complex structure does.
Okay.
Now add in a way to measure distances and angles that's compatible with this rotation,
Okay.
and you're getting closer to the idea of an almost Hermitian structure.
So it's like we're adding extra geometric structure to the blow-up.
Exactly.
A structure that plays nicely with these rotations.
Yes.
But how do the non-abelian monopoles fit into this picture?
Good point.
And while you're at it, could you remind me what makes these monopoles non-abelian?
Let's step back a bit.
Okay.
In physics, a monopole is a hypothetical particle with only one magnetic pole.
Right.
While they haven't been observed in nature,
Right.
they pop up in theoretical physics,
Okay.
particularly in gauge theory,
Right.
which is a framework for understanding forces.
Right. I remember learning about gauge theory.
Yeah.
It's all about symmetries and how they dictate the interactions between particles.
Exactly. Now, these monopoles we're talking about are mathematical objects that share some key properties with their physical counterparts.
Okay.
But they live in the realm of gauge theory with a non-abelian gauge group.
Okay.
In simpler terms, the order in which you perform certain operations within this group actually matters.
Right.
This is unlike the more familiar abelian groups like addition, where the order doesn't change the outcome.
So non-abelian basically means things get a lot more intricate and intertwined.
Exactly.
Yeah.
And these non-abelian monopoles play a crucial role in this proof strategy
Right.
because they provide a bridge between the almost Hermitian structure on the blow-up and the topological invariants we're interested in.
Okay.
Each point in this moduli space we've been talking about actually represents a different non-abelian monopole.
So the moduli space is like a map or a catalog of all possible non-abelian monopoles, and we're giving this space an almost Hermitian structure to study it more effectively.
Precisely by analyzing the geometry of this moduli space, particularly how the almost Hermitian structure interacts with it.
Right.
The authors of these excerpts aim to derive the Bogomolov-Mijalka-Yau inequality on the blow-up.
This is where I start to get a little fuzzy.
Sure.
What does it even mean for an inequality to hold on a moduli space? It feels very abstract.
Good question. It's about using the geometry of the moduli space to extract information about those topological invariants.
Okay.
The excerpts suggest that by analyzing a special function on the moduli space,
Right.
the Hamiltonian,
Okay.
we can relate its critical points to solutions of something called the Seiberg-Witten equations.
Okay.
These equations are another tool from gauge theory, and their solutions are deeply connected to the topology of four manifolds.
Okay, so we've got these non-abelian monopoles, their moduli space, equipped with an almost Hermitian structure, a Hamiltonian function,
You're right.
and these Seiberg-Witten equations lurking in the background.
Yes.
It's like a whole toolkit of sophisticated mathematical gadgets.
Sure.
But how do we actually use them to prove the Bogomolov-Mijalka-Yau inequality on the blow-up?
That's where things get even more interesting.
Okay.
The excerpts mention a specific condition called the Morgan-Rocha condition,
Okay.
which seems to play a crucial role in connecting these different pieces.
Okay.
But before we dive into that, perhaps we should take a closer look at this blow-up construction itself.
I agree. Let's make sure we have a firm grasp on the foundation before we build the rest of the house.
Okay.
The excerpts mention something about a ruled complex surface, $6
Right.
that fibers over a Riemann surface, sigmig, of genus $.
Right.
They also mentioned that the Bogomolov-Mijalka-Yau inequality fails when data YAG 22.
Right.
I'm guessing this example is important for understanding the limitations of the inequality.
Absolutely. It highlights that the Bogomolov-Mijalka-Yau inequality isn't some universal truth that holds for all four manifolds.
Right.
Its validity depends on the topology of the manifold, and this example illustrates a case where it fails. This failure gives us insight into the boundary cases and subtle nuances of the inequality, which is often where the most interesting mathematics lies.
That makes sense. So we're dealing with a specific type of four manifold,
Yeah.
and we're blowing it up to create a new space where the inequality might be easier to prove,
Right.
but the blow-up itself isn't arbitrary, is it?
Right.
There are choices involved, like the choice of a cohomology class to override.
You're exactly right. The details of the blow-up construction are incredibly important.
Okay.
The excerpts mention a specific choice for this cohomology class.
Right.
That satisfies a condition involving two Malers x and an integer $.
Okay.
This choice seems to be crucial for ensuring that the proof strategy works.
This is reminding me of those intricate proofs where every little detail, every carefully chosen object, plays a specific role in the grand scheme of things.
Yes.
I have a feeling we're in for a wild ride.
You're not wrong, but that's what makes this depth dive so fascinating.
Right.
We're about to unravel a complex and elegant argument,
Right.
piece by piece.
Lead the way. What's the next piece of this puzzle?
Well, to understand why this particular choice of W is so important, we need to delve into the world of spin-sack structures and spinda structures.
Okay.
These structures provide the framework for defining the Seiberg-Witten equations and the non-Abelian Monopoles equations,
Okay.
which, as we've discussed, are key to this whole proof strategy.
Okay, spin structures. Now, those always did make my head spin a bit, even back in grad school.
Right.
Perhaps you could remind me and our listeners what these structures are all about.
Sure.
And why they're so essential in this context.
You're right. Spin structures can be a bit mind-bending. Think of them as a way to consistently define the notion of spinning on a manifold in physics. Spin is an intrinsic property of particles. But in this context, we're talking about abstract mathematical objects that capture a similar idea.
Right, it's like we're taking a concept from physics and giving it a purely mathematical interpretation.
Exactly. Now, a spin structure is a bit more intricate. It's like a twisted version of a spin structure, allowing us to define these spinning objects on manifolds that might not admit ordinary spin structures.
So it's like we're relaxing the requirements a bit to work with a broader class of manifolds.
Precisely. And this extra flexibility is crucial for defining the Seiberg-Witten equations, which are a set of equations involving a spin structure and a connection on a line bundle over the manifold.
Okay, so the spin structure gives us the framework for these Seiberg-Witten equations, which are somehow connected to the topology of the four manifold. But what about the spin structure mentioned in the excerpts? How do they fit into this picture?
Spin structures are even more general than spin structures. They're like the big siblings that allow us to work with connections on higher rank vector bundles, not just line bundles. And this generalization is essential for defining the non-abelian monopole equations.
So it's like we have this hierarchy of structures, spin, then spin each one, providing the necessary framework for a more general type of equation. The spin-Rasa structures give us the Seiberg-Witten equations, and the spin structures give us the non-abelian monopole equations.
You've got it. And the beauty of this approach is that these structures and equations are deeply intertwined. The solutions to the Seiberg-Witten equations are intimately related to the solutions to the non-abelian monopole equations, especially for these split monopoles that we're interested in.
It's amazing how everything seems to be connected. But let's get back to the proof strategy you mentioned earlier, that this Morgan-Roca condition plays a crucial role. What is this condition, and how does it help us bridge the gap between the blow-up and the original form manifold?
The Morgan-Roca condition is a bit technical, but essentially it's a topological condition on the spin-null structure we choose on the blow-up. This condition ensures that the moduli space of non-abelian monopoles on the blow-up is well-behaved and has the right properties for the proof to work.
Well-behaved, in the sense that it allows us to relate the inequality on the blow-up back to the original manifold.
Precisely. It's like ensuring that the scaffolding we've erected is stable enough to support the weight of the argument without this condition. The moduli space could be too wild and untamed for us to extract any meaningful information.
That makes sense. We need to make sure we're working with the right kind of moduli space, one that's compatible with our goals. The excerpts delve into quite a bit of detail about the properties of this Chaisin spin-knot structure, particularly how it interacts with the cohomology class flow. It seems they're building a very specific and delicate structure here.
You're absolutely right. It's like they're carefully laying the groundwork for a complex mathematical construction. They want to ensure that every piece fits perfectly so that the entire argument holds together.
And speaking of fitting together, the excerpts mention a specific quadratic form denoted by CARX, right again where it represents the blowup of our ruled complex surface.
Yeah.
What is the role of this quadratic form in this intricate construction?
That quadratic form is a powerful tool for analyzing the properties of the spin-1 structure and its relationship to the cohomology class. So remember, we're trying to choose $dollars so that the moduli space on the blowup is well-behaved well. This quadratic form helps us translate those desired properties into concrete algebraic conditions.
So it's like we're using algebra to get a handle on the topology of the situation. I always love when different fields of mathematics come together like this.
Me too, and this is a prime example of how those connections can be so fruitful. The excerpts mention a specific formula for Ka-X, which involves several variables related to the topology of the form manifold and the blowup. By carefully choosing those variables and analyzing the properties of tar-X, the authors ensure that the chosen dollar satisfies the Morgan-Roca condition.
Okay, so this quadratic form is like a telling ground for our choice of W. If it passes the test, our moduli space is in good shape. But the excerpts then dive into some pretty heavy computations involving CoRX, the cohomology class is a spin structure, and our chosen dollar was the purpose of these calculations.
Those calculations are the heart of the argument for this specific case. Remember, the authors are working with a ruled complex surface dollars that fibers over a Riemann surface. The computations show that with their carefully chosen Wx, the value of the quadratic form, Quadrio W, can be made arbitrarily large by adjusting certain parameters.
And why is that significant? What's the big deal about making this quadratic form large?
That's where the connection to the Bogomolov-Miyaoki-Yau inequality comes in the fact that we can make Quadrex C1SS arbitrarily large implies that a certain quantity related to the numerical invariance C12 $2 must also be large, and this combined with other properties derived from the choice of dollar ultimately leads to the inequality on the blowup.
I see. So by carefully manipulating these algebraic objects and exploiting the properties of the chosen spin disk structure, we're essentially forcing the Bogomolov-Miyaoki-Yau inequality to hold on the blowup. It's like we're strategically setting up the game board so that the inequality has no choice but to win.
That's a fantastic way to put it, and that's the beauty of this proof strategy. It's about using these sophisticated mathematical tools, the spin structures, the quadratic form, the careful choice of white to construct a situation where the inequality emerges naturally from the structure of the moduli space.
It's truly remarkable how these seemingly abstract concepts can be combined to tackle such a concrete problem about the topology of four manifolds. It's like we're using a microscope to examine the intricate machinery of the universe at the most fundamental level.
I couldn't agree more, but this is just the beginning. The excerpts go on to discuss the canonical spin-saw structure and how it relates to the Seiberg-Witten and non-Abelian monopole equations in even more detail. They then dive into the world of differential geometry, introducing connections, curvature, and the Hodge star operator. It seems we're about to journey even deeper into the heart of this proof.
Lead the way. I'm ready for the next adventure.
Okay.
So we're picking up this thread of this proof, and we're about to delve deeper into the world of differential geometry, connections, curvature, Hodge star operators.
Yeah.
These are all tools for understanding the geometry of manifolds on a deeper level.
Right.
What's the game plan here?
Okay, so
How do these tools help us bridge the gap between the algebraic manipulations we've seen so far and the topological conclusion we're aiming for?
you're right. We're transitioning from the more algebraic setup to the analytical tools needed to cement the argument.
Okay.
The excerpts begin to unpack the specifics of the Seiberg-Witten and non-Abelian monopole equations, particularly how they look in the context of an almost Hermitian four-manifold.
Right, because we've given our blow-up that special almost Hermitian structure, so it makes sense that we'd want to leverage that choice.
Right.
But these equations, even in their standard form, are not exactly lightweight.
Yeah.
They involve spinors, connections, curvature, and all sorts of other geometric gadgets.
Right.
How does the almost Hermitian structure make them any easier to work with?
The almost Hermitian structure provides a way to express these equations in a more convenient form using differential forms,
Right.
which are a bit more user-friendly than spinors, at least in this context.
Oh.
It's like switching from a more abstract language to a language that's more directly tied to the geometry of the manifold.
Ah, so it's like a change of coordinates that simplifies the equations and makes their geometric meaning more transparent?
Exactly. And that's a common theme in mathematics.
Right.
Finding the right perspective, the right language
Right.
that allows you to unlock the secrets of a problem.
Absolutely. The excerpts mention several operators like partial Mang, partial Lanny-Bay, and their adjoints,
Right.
which appear in these rewritten equations. I'm guessing these operators capture different aspects of the connection and the curvature.
Yeah.
But how do they all fit together in this grand scheme?
You're right. Those operators encapsulate the essential information about the connection and its curvature.
Okay.
They're like the building blocks of a delicate machine, each one playing a specific role in the overall function of the equations. And the specific relationships between them, as outlined in the excerpts, are crucial for deriving the estimates needed to control the solutions.
Estimates. Sounds like we're heading into analysis territory now.
Yeah.
Why do we need to estimate these solutions?
Excellent question. Remember, we're ultimately interested in proving an inequality.
Right.
To do that, we need to get a handle on the size and behavior of these solutions, and that's where the analytical tools come into play.
Right. We can't just wave our hands and say, oh, these solutions exist and they behave nicely, so the inequality must hold.
Right.
We need rigorous quantitative control over these solutions, which is where these estimates come in.
Exactly, and the excerpts mention specific differential inequalities that provide these crucial bounds. These inequalities are analogous to those developed by Taubes for the Seiberg-Witten equations,
Right.
but they're adapted to the more general setting of non-Abelian monopoles.
Taubes' work has been incredibly influential in this area. It's amazing to see how his ideas continue to ripple through different areas of gauge theory. But these non-Abelian analogs must involve quite a bit of technical machinery. How do we even begin to derive such inequalities in this more complex setting?
You're right, it gets quite technical.
Yeah.
But the core ideas are similar to those used in the Seiberg-Witten context. We start by analyzing the Bochner-Weizenbuch formula,
Okay.
which relates the Laplacian of a spinor field to the curvature of the connection and other geometric data.
Ah, the Bochner-Weizenbuch formula, like a Swiss Army knife for differential geometers, always seems to come in handy.
Right.
But how does it apply in this specific situation?
The Bochner-Weizenbuch formula in this context allows us to derive a differential inequality that relates the Laplacian of the norm squared of the spinor field to the curvature of the connection and the scalar curvature of the manifold.
Okay.
This inequality is the starting point for deriving Taubes' differential inequalities.
So it's like a blueprint for controlling the behavior of the spinor field.
Precisely by manipulating this inequality and using other geometric tools such as the Kähler identities in the almost Kähler case, we can derive bounds on the growth of the spinor field.
The excerpts mention a pointwise estimate for the holomorphic component of the spinor field denoted by a binary field.
Right.
What's the significance of this estimate?
That estimate is a crucial ingredient in the proof. It tells us that the magnitude of the holomorphic component of the spinor field can be controlled by the curvature of the connection and other geometric data. This control is essential for ensuring that the moduli spaces are well-behaved and have the expected dimensions.
It sounds like we're building a chain of logic here,
Yes,
with each estimate providing a tighter constraint on the solutions.
exactly. Each step in the argument builds on the previous one, gradually tightening the net around these solutions and forcing them to reveal their secrets.
And I'm guessing that the strong maximum principle, which the excerpts mention, plays a crucial role in this process.
You're spot on. The strong maximum principle is a powerful tool that allows us to control the behavior of solutions to elliptic differential equations, which is precisely what we're dealing with here in this context. It helps us establish global bounds on the solutions from local information.
Right, because these differential inequalities give us local control over the solutions.
Right.
But we need global control to prove something about the entire manifold.
Exactly. The strong maximum principle provides the bridge between the local and the global. It allows us to say that if a solution satisfies certain conditions locally, then it must also satisfy certain bounds globally.
And those global bounds are what ultimately allow us to prove the Bogomolov-Miyakoyao inequality.
You got it. It's a long and winding road.
Right.
But each step in this proof strategy is carefully designed to bring us closer to that final goal.
Okay.
By combining sophisticated geometric tools, analytical estimates, and topological arguments, we can finally bridge the gap between the world of non-abelian monopoles and the world of complex four manifolds.
This has been an incredible journey. We've seen how the authors of these excerpts have woven together ideas from topology, geometry, and analysis to create a truly remarkable proof strategy. But it feels like we've just scratched the surface. The excerpts hint at so many open questions and potential extensions of these ideas.
Absolutely. This is an area of active research, and there's still so much we don't know about these fascinating mathematical objects and their interconnections. This deep dive has given us a glimpse into the intricate machinery of the universe at the most fundamental level, but it's also left us with a sense of wonder and a thirst for further exploration.
Well said. It seems the journey never truly ends.
That's right.
Only the destinations change. And on that note, we'll leave our listeners to ponder the mysteries that still lie hidden within the elegant structures of mathematics. Okay, so today we're really diving deep, headfirst, into this world of almost Hermitian structures. And of course, we've got the non-abelian monopoles, and then we're going to see how they kind of come together and tell us something about the topology of four-dimensional spaces, which is always fun.
Always a good time.
Yeah. So we've got, this is some dense mathematical research we're looking at today. Excerpts from almost Hermitian structures on Moduli spaces of non-abelian monopoles and applications to the topology of symplectic four manifolds. So, yeah, buckle up.
It's fascinating how this research really gets into a very specific area where all these different mathematical concepts kind of come together.
Yeah, and right from the get-go, they're already talking about how the moduli space of non-abelian monopoles, particularly near, regular points, inherits this structure that behaves remarkably like a smooth manifold with an almost Hermitian structure.
And that's really just the start. What's interesting is how they bring in Frankel's theorem into this whole picture, because we're essentially dealing with points in this moduli space that have non-vanishing coupled spinors.
Ah, yes. Spinors. Right, we've seen those before.
Right.
It feels like we're piecing together like a mathematical jigsaw puzzle, and every time we do one of these deep dives, it's like we unlock or we uncover another piece, and we're like, okay, I see how this fits into the bigger picture.
Exactly. And this is where it starts to unravel some really intriguing questions, I think. For instance, they bring up the curious case of ruled complex surfaces and how they seemingly, at least, defy this, pretty fundamental idea in algebraic geometry, the Bogomolov-Miyakoyao inequality.
It's like, okay, what is it about these ruled complex surfaces that make them break the rules? What's the deeper significance of that kind of deviation?
That's the kind of question that, pushes mathematical inquiry forward, right? Because this apparent contradiction or this inconsistency maybe points to something deeper, some deeper connection between these different areas of mathematics that we haven't quite uncovered yet. And it's often these sorts of inconsistencies that can lead to some really big breakthroughs, right?
Yeah, absolutely. So we've got these rule-breaking surfaces to contend with. And then, to add to the complexity, they introduce the Taub's perturbed non-abelian monopole equations. Which sounds very
A
intimidating.
little bit,
It
yeah.
feels like we're entering a whole new level of mathematical abstraction.
Definitely. But these equations, while complex, are really essential tools for understanding the behavior of these monopoles and how they interact with the surrounding space. You can kind of think of them like a lens through which we can really examine these structures in much greater detail.
Right. Okay. So we're given this new tool, this new lens to kind of like zoom in and really start to analyze. And then they go into Donaldson's symplectic subspace criterion,
Right.
which is like this key theorem in this area.
Yeah.
But they don't stop there.
They don't.
They're like, okay, we're going to take this theorem, but we're going to generalize it.
Exactly.
So it's applicable to a much larger class of mathematical objects. In this case, we're talking about bounded real linear operators on complex Hilbert spaces.
Which, is a mouthful in itself. But it essentially allows us to apply this theorem, this very powerful tool, in many more situations, right?
Yeah, it's like they're giving us a more powerful tool to work with.
Exactly.
And it's at this point that this idea of a circle action, this circle action within these complex spaces comes into play.
Exactly.
What does that even mean?
Yeah, it's a very, abstract concept to wrap your head around. But essentially, by examining how, rotations behave in these very abstract settings and focusing on what are called fixed points, the points that remain unchanged by the rotation, we can gain valuable insight into the geometry of these spaces, and particularly their relationship to these Seiberg-Witten monopoles.
Seiberg-Witten monopoles, there they are again.
Pop up everywhere.
I swear that those are like the recurring character in our mathematical journey here.
They are fundamental to this entire area of research. Absolutely. And this is where the paper really kind of takes a deep dive into this very, rather intricate concept called virtual Morse-Bott indices, which sound very intimidating.
They do sound very intimidating. And I think it's important for us to clarify here. These indices are crucial for us to actually be able to understand the topology of these spaces.
They are.
But for someone who's maybe not as familiar, what do we even mean by indices? Why are they important in this specific context?
Right. So in a nutshell, these indices provide us with a way to sort of classify and compare these complex shapes based on their very fundamental topological properties, the things that don't change when you stretch or bend them, for example.
Right.
So regardless of their exact size or shape, it's more about the fundamental structure, right?
So like the number of holes in a donut, regardless of what kind of donut it is.
Precisely. That's a great analogy.
Okay. So we're getting down to the core essence of these shapes.
Exactly. And to actually calculate these indices, they turn to another very powerful tool, which is the Atiyah-Singer index theorem.
Ooh.
And this theorem is really like a cornerstone of modern mathematics because it bridges this gap between analysis, which deals with things like continuity, limits, and topology, which we've been talking about.
So it's like a mathematical Rosetta Stone.
Exactly.
We're able to translate between these two different but related areas of math.
Absolutely. And in this case, the Atiyah-Singer index theorem is the bridge between the analytical properties of the equations that we're using to describe these monopolars and the topological information that we're actually trying to extract from them.
I love that because it shows that we're not just dealing with like these equations in isolation, right?
Right.
We're using all these different mathematical tools, all these different concepts, and they all kind of weave together to tell us something much more profound.
They're all interconnected, and that's what makes this research so fascinating.
Yeah, I agree.
It highlights how everything kind of fits together in this beautiful tapestry of mathematics.
I'm ready to keep going.
Let's do it. So we're really focusing on a very specific type of non-abelian monopole here. And the Atiyah-Singer index theorem helps us calculate those virtual Morse-Bott indices within this very specific context.
Okay, so we're really fine-tuning this powerful theorem to address a very particular mathematical puzzle.
Exactly. And these calculations are not for the faint of heart, but the insights we gain are well worth the effort, I assure you.
Lead the way. I'm eager to see how this unfolds.
All right, so one of the core concepts we need to grasp here is this distinction between what's called the Morse-Bott index, the Co-Index, and the nullity.
Okay.
These three values, when considered together, provide us with a more holistic picture of the function's local behavior around its critical points.
I see. So it's like we're doing like a detailed dissection of these critical points
Yes.
to understand their inner workings. And these indices are like the key anatomical features that we're looking for, right?
Yeah. Precisely. You can think of the index as a measure of the number of independent directions in which the function decreases, the co-index as the number of directions in which it increases, and then the nullity kind of represents the directions where it remains flat, so to speak.
Okay, so we're essentially constructing this like three-dimensional map of the function's behavior around these critical points. But how does this then connect to our non-abelian monopoles?
Right. So the paper examines something called Hitchin's Hamiltonian function,
Okay.
which is a key element in describing the dynamics of these monopoles. Calculating the virtual Morse-Bott indices for this function at a specific type of monopolars gives us deeper insights into how these objects actually behave within their moduli space.
So it's like we're generating this like dynamic map of this mathematical landscape, highlighting the features that dictate how these monopolars, move and interact with each other.
That's a great way to put it. And this brings us back to that concept of circle action that we discussed earlier.
Right.
Remember those fixed points?
The points that stay put during the rotation, right?
Yeah, exactly. Those fixed points actually correspond to Seiberg-Witten monopolies. And intriguingly, there's a very crucial relationship between these monopolies and those virtual Morse-Bott indices.
So we're not just dealing with abstract shapes here. These indices are directly linked to these fascinating Seiberg-Witten monopolies. It's like we're using these calculations to pinpoint their location on our mathematical map.
Precisely. And the paper goes into quite a bit of detail about the explicit calculation of the virtual Morse-Bott index for Hitchin's Hamiltonian function at a what's called a non-zero section split non-abelian monopoly.
Okay.
Now, this calculation involves applying the Atiyah-Singer index theorem to something called the deformation operator of the perturbed non-abelian monopoly equations.
That sounds incredibly complex. Could you break that down for me a bit?
Right.
What is the deformation operator, and how does it fit into this whole picture?
Sure. So in essence, you can think of the deformation operator as a way to describe how the solution to the monopole equations changes when we slightly perturb the initial conditions, so to speak. Applying the Atiyah-Singer index theorem to this operator allows us to link its analytical properties to the topological information encoded in those virtual Morse-Bott indices.
I see. So it's a very indirect but remarkably powerful approach. We're analyzing these subtle ripples caused by these perturbations and using them to map the underlying structure of the space.
Exactly. You've got it. And what's remarkable is that the paper actually provides us with explicit formulas for the virtual Morse-Bott index, the co-index, and the nullity at these particular types of monopoles.
Okay.
And these formulas really beautifully illustrate the relationship between the topological invariance of the underlying four-manifold and the properties of these line bundles that are associated with this split non-abelian monopole.
It's like these formulas are the missing pieces of a complex puzzle, aren't they?
They really tie everything together,
Yeah.
and they do so in a very elegant way.
It's fascinating how we're using these like complex calculations to actually simplify our understanding of these objects. It's like we're peeling back layers of complexity to reveal these like really elegant core principles at play.
That's the beauty of mathematics, isn't it? And this simplification has profound implications because it allows us to connect the behavior of these monopolars to those fundamental topological invariants that we talked about, providing a deeper understanding of the geometry and topology of four manifolds.
I love how this research is like this bridge between these different areas of mathematics, revealing these unexpected connections and these like really profound insights.
It really highlights the interconnectedness of it all, doesn't it?
It does.
And we're not even done yet. The paper goes even further. It delves into this concept of reducible connections and how they relate to the structure of the moduli space. This takes us deeper into gauge theory, which is a powerful framework for understanding the fundamental forces in physics, by the way.
Oh, okay. So are you suggesting that these abstract mathematical concepts might have real-world applications?
Absolutely. By investigating the properties of these reducible connections, which are essentially connections that can be kind of broken down into simpler components, we gain a deeper understanding of the topology of the moduli space and ultimately how it relates to the underlying four-manifold.
So we're like breaking these complex connections down into their fundamental building blocks.
That's right.
To understand how they contribute to the larger structure.
Precisely. Now, the paper takes us through this very detailed proof of the existence of a circle invariant, non-degenerate two-form on the moduli space. And this proof relies on this powerful generalization of Donaldson's symplectic subspace criterion and an analog of Paubs's pointwise estimate for solutions to the perturbed Seiberg-Witten monopole equations.
It seems like there's a recurring theme here of like taking these established mathematical tools and pushing them further, expanding their scope and power to be able to tackle these increasingly complex problems.
That's what mathematicians do, right? We're always pushing the boundaries of what's possible.
Always innovate.
Exactly. And this particular proof, while it is quite intricate, involving a lot of careful analysis of operators and Hilbert spaces, it ultimately establishes this critical link between the geometry of the moduli space and the underlying four-manifold.
It's like we're building this mathematical bridge between these two worlds, allowing us to traverse back and forth and gain this much deeper understanding of both.
That's a great way to visualize it. Now, let's dive a bit deeper into the analysis of these operators and their properties, shall we? The paper introduces this concept of what's called approximately complex deformation operators,
Approximately complex deformation operators. Okay.
which are instrumental in understanding the structure of the moduli space.
So what makes these operators so special? How do they contribute to our understanding of the moduli space?
These operators essentially give us a really convenient framework for studying what's called the deformation complex of the moduli space. Think of them as a tool that allows us to break down this complex structure into more manageable components, making it easier to analyze and extract meaningful information.
So it's like a divide and conquer strategy, but applied to these complex mathematical structures.
Exactly. And the paper goes through a very meticulous construction of these operators, outlining their key properties, how they relate to the standard deformation complex, and it delves into the specific forms of what are called the harmonic spaces associated with these operators,
Right.
which in essence are the spaces of solutions that remain unchanged under certain transformations.
So they're like these anchor points in our analysis, providing stability within this complex system.
Exactly. And understanding these spaces is key to understanding the overall structure of the moduli space and its intricate connection to that underlying four-manifold.
Yeah, I'm consistently amazed by just the level of detail and the complexity involved in this research. It's like we're exploring this vast and intricate network of mathematical concepts,
It really is.
and each one seems to lead to these new insights and discoveries.
And we're not even close to exhausting all the really interesting things in this paper. It goes on to examine the Taub's perturbed non-Abelian monopole equations in even greater detail, deriving these really crucial estimates and inequalities that shed light on the behavior of solutions.
So now we're going really deep into like the analytical core of this area of research.
We are.
And we're using these equations to extract like really precise information about these elusive monopoles.
Oh, and it actually draws some really interesting parallels between these estimates and those that Taubes himself derived for solutions to the perturbed Seiberg-Witten monopole equations. So these are very valuable tools for understanding these solutions and how they relate to the geometry of the four-manifold.
So we're building on that foundation that was laid by Taub's work
Yeah.
and extending those methods and insights to this new realm of non-abelian monopoles.
Precisely. And that's how scientific progress works, right? We build upon the work of the giants who came before us.
Absolutely. Now, the paper also touches upon this concept of Kunishi model neighborhoods. Can you shed some light on what those are? Why are they important?
Right. So you can think of Kuranishi model neighborhoods as local charts, in a way, that provide a way to describe the structure of the moduli space near a given point. It's like, imagine you have a map of a very complex terrain. These neighborhoods are like zoomed-in maps that reveal the intricate details of specific regions.
Okay, so instead of trying to grasp the entirety of this complex space all at once, we're breaking it down into smaller, more manageable regions.
Precisely. And this is very valuable because it allows us to use tools from differential geometry, which deals with smooth manifolds, to study the properties of this moduli space, which might not be a smooth manifold globally.
So it's like we're employing this more focused approach, using these tools from differential geometry to really examine those fine details of this structure.
Exactly.
Now, aside from just providing these like localized views, what other insights do these Kuranishi model neighborhoods help us uncover?
Well, the paper goes into detail about the construction of these neighborhoods, highlighting their key properties and how they contribute to our understanding of the overall structure of the moduli space. It also explores the smoothness of that non-degenerate two-form that we talked about earlier on these neighborhoods, ensuring that our geometric analysis remains valid even at this very localized level.
It's like we're making sure our map is still consistent and accurate, even when we're zoomed in on a very specific region.
Exactly. A good map is crucial, right?
Absolutely.
Now, the paper does conclude by kind of acknowledging some limitations of this approach and outlining potential avenues for future research, emphasizing that these findings are, specific to four-dimensional, almost Hermitian manifolds, and further investigation is needed to extend these results to more general settings.
So while this research has made significant advances, it also recognizes that the journey of mathematical discovery is ongoing.
Always.
There's always more to explore.
Absolutely. That's what makes it so exciting, right? It's this constantly evolving landscape with new discoveries and insights emerging all the time.
Yeah, I love that.
And this paper serves as a really robust foundation for future research, providing a really, really solid framework for delving even deeper into this intricate world of almost Hermitian structures, non-abelian monopoles, and their applications to the topology of four-dimensional spaces.
Well, this has been a truly enlightening journey. We've navigated through some seriously dense mathematical concepts. But I think what's really remarkable is how this research connects these seemingly abstract ideas to these potentially profound implications for our understanding of the universe itself.
It really highlights the power of abstract reasoning, right?
It does.
To illuminate these fundamental truths about the physical world.
Yeah. Well, thank you so much for being such an insightful guide through this challenging yet absolutely fascinating terrain. I always appreciate our time together.
It's always a pleasure.
And until next time, may your explorations continue to be filled with wonder and discovery. Okay, ready to dive into some seriously fascinating math.
Always up for a good mathematical challenge. What are we tackling today?
We're looking at this paper, Almost Hermitian Structures on Moduli Spaces of Non-Abelian Monopoles and Applications to the Topology of Symplectic Four Manifolds.
Oh, wow. Right from the title, it's clear we're not messing around. This is some high-level stuff.
You got that right, and that's why we're here, to unpack it all.
Sounds good to me. Where do we even begin with something like this?
Well, for this deep dive, I thought we could really focus on the core proofs in this paper. They seem to be the crux of the whole thing.
Agreed. The proofs are where all those abstract concepts become concrete. But before we jump into that rabbit hole, how about a quick overview of the key players, just to make sure everyone's on the same page,
Right. Always a good idea. So we've got almost Hermitian structures, moduli spaces, and of course those symplectic four manifolds.
Yeah, those are the big ones. Let's start with almost Hermitian structures. Basically, it's a way to give a smooth manifold a certain type of geometric structure. As the name suggests, it shares a lot of similarities with Hermitian structures, but with a bit more flexibility.
Right, a bit more relaxed, as it were. Now, how do those structures connect with these moduli spaces? If I'm remembering correctly, we're essentially talking about spaces where each point represents a different mathematical object, right?
You got it. And in the case of this paper, those objects are non-abelian monopoles.
Non-abelian monopoles, those are like those hypothetical particles in physics, right?
Yeah.
Magnetic monopoles, but with a more complex structure.
Exactly. Imagine them as having multiple poles instead of just a simple north and south. This paper's Moduli Space is essentially cataloging all the possible configurations of these non-abelian monopoles.
Okay, starting to piece it together. So we're taking these almost Hermitian structures and applying them to this catalog, this Moduli space of non-abelian monopoles, almost like we're analyzing the geometry of their possible configurations.
A great way to put it. And that's precisely what the paper delves into.
I see, I see. And how do those symplectic four manifolds come into play?
Ah, yes, a crucial piece of the puzzle. Simply put, a symplectic four manifold is a four-dimensional space equipped with a special kind of geometric structure called a symplectic form. It's like having a way to measure areas and volumes that's specifically tailored to that space's geometry. Incredibly important in both math and physics, by the way.
Right. Can't forget about those physics connections. Okay, so just to recap, we have almost Hermitian structures giving us a framework. We have moduli spaces acting as our catalog of non-abelian monopoles. And all of this is happening within the realm of symplectic four manifolds. Did I miss anything crucial?
Nope. I think you've summarized it perfectly. Ready to dig down to the nitty-gritty of the proofs themselves?
Absolutely. Let's do it. All right, let's get into these proofs. This is where things get really interesting.
It's where the abstract meets the concrete, and this paper has some seriously elegant proofs.
I like the sound of that.
Yeah.
So what's the first proof we're tackling?
Well, the paper kicks things off with Frankel's theorem. Specifically, they're using a version that applies to circle actions on almost Hermitian manifolds.
Okay, a couple of things to unpack there. We talked about almost Hermitian manifolds earlier, but what exactly do they mean by circle actions?
Imagine you're rotating an object in space, like spinning a basketball on your finger. That's basically a circle action. You're moving every point on that object along a circle.
Got it. So it's all about rotation. But we're doing this to our almost Hermitian manifold, right?
Exactly. A circle action in this case is a way to smoothly rotate or act on that manifold without, breaking its inherent geometric structure.
So we're spinning our manifolds, but in a way that respects its geometry. Okay, makes sense. Now, what does Frankel's theorem actually tell us about these rotating manifolds?
Good question. Essentially, it helps us identify those special points that don't move during the rotation, the critical points.
The points that stay put amidst all the chaos.
hmm
Interesting. And why are those critical points so important?
Well, in the context of this paper, those critical points within our moduli space of non-Abelian monopoles, they turn out to be key to understanding the topology of the whole space.
So those stationary points hold valuable information about the overall structure. That's pretty cool. What's next on our proof decoding adventure?
Next up, the paper takes on quite a challenge. They generalize Donaldson's symplectic subspace criterion.
Donaldson. Now, that's a name that carries some serious weight in the world of symplectic geometry. What's so special about this criterion?
Donaldson's work is pretty groundbreaking. His criterion gives us this powerful tool to determine if a space contains a smaller space within it, a submanifold that also has a symplectic structure.
So like a test for symplectic submanifolds.
Yeah.
Why is that important in this context?
Remember how we talked about symplectic structures giving us a way to measure areas and volumes in a way that aligns with the space's geometry?
Right, like a special ruler for curved spaces.
Exactly. Donaldson's criterion helps us figure out where those special rulers apply within a larger space.
Makes sense. So how does this paper build upon Donaldson's work?
Well, they generalize it. They take his criterion, which was initially designed for finite dimensional spaces, and they extend it to work in the realm of Hilbert spaces.
Hilbert spaces, those are those infinite dimensional vector spaces, right? It's like they're taking a tool designed for a small workshop and scaling it up to work in a massive factory.
A very apt analogy. And the implications of this generalization are significant. It gives us a much deeper understanding of the structure of certain moduli spaces, especially those related to, you guessed it, non-Abelian monopoles.
It's all connected. I'm starting to see the web they're weaving here. What other mathematical marvels await us in this paper?
Well, this is where things get particularly intriguing. The paper goes on to prove that all those non-zero critical points we've been discussing, the ones revealed by Frankel's theorem, they're all represented by a very specific type of monopole, Seiberg-Witten monopoles.
Hold on, are we saying those fixed points, those unmoving points during our mathematical rotations, they all correspond to Seiberg-Witten monopoles?
Exactly. And that's a huge deal. It reveals a very deep connection between these different types of monopoles, a connection that wasn't known before.
It's like finding a hidden passageway between two seemingly separate rooms in a massive mathematical mansion. I love it. What else is on the menu for today's Proofalicious Deep Dive?
They don't stop there. The paper dives into the virtual Morse-Bott signature of a particular Hamiltonian function.
Okay, now that sounds like a mouthful, even for seasoned math fans like ourselves. What in the world is a virtual Morse-Bott signature?
I know, right? It's a mouthful. Essentially, Morse theory, in general, gives us a way to understand the shape, the topology of a space by studying the critical points of a function defined on that space. Like, imagine looking at the peaks and valleys of a mountain range to understand its overall form.
Okay, that makes sense. So the peaks and valleys represent those critical points.
Right. Now, the virtual and bot aspects add some layers of complexity, allowing us to apply these ideas in more abstract and general settings.
So we're analyzing the peaks and valleys of a mathematical landscape to understand its hidden structure. And in this case, that landscape is our moduli space of non-Abelian monopoles.
You've got it. By calculating this virtual Morse-Bott signature, the paper uncovers some very subtle yet profound properties of the moduli space itself. It's really quite remarkable.
It sounds like we've successfully navigated our way through a jungle of proofs. We've uncovered hidden connections, explored groundbreaking theorems, and even deciphered the secrets of virtual Morse-Bott signatures. But how does it all fit together? What's the big picture story these proofs are telling us?
So we've gone through these intricate proofs, each one like a piece of a puzzle. And now it feels like it's time to see how it all comes together.
Right. It's not just about the individual proofs, but how they connect to reveal a bigger picture. It's like we've built this intricate machine, and now we get to see it in action.
Exactly. So how do these proofs, particularly when it comes to gauge theory, all come together? This is where things get really exciting. Remember how gauge theory underpins our understanding of fundamental forces in physics? Well, this paper subtly shows how these geometric structures, almost Hermitian structures, the moduli spaces, they give us this powerful new lens through which to view and study gauge theory.
So we're bridging the gap between abstract geometry and the physical world.
Precisely. And it's through these proofs, these intricate mathematical arguments, that this bridge is built piece by piece. Frankel's theorem zeroes in on those crucial points in our moduli space. Then, that generalized Donaldson criterion that gives us a deeper understanding of its structure. And then, boom, the link to Seiberg-Witten monopoles. It's like suddenly we're seeing a connection to this powerful theory in physics.
And let's not forget about that virtual Morse-Bott signature. It's like we're given a toolkit to analyze those moduli spaces in a way we couldn't before.
Absolutely. Each proof is like adding a new tool to our kit, a new way of understanding. And it highlights how interconnected mathematics truly is. What might seem like different areas, geometry, topology, gauge theory, they're all related, all part of the same grand tapestry.
It's pretty awe-inspiring when you think about it.
Yeah.
So for our listeners out there who are ready to really dive deep into this paper, what would you say are the biggest aha moments they should keep in mind?
Well, first off, this paper really showcases the power of generalization in mathematics. By taking existing tools like Donaldson's criterion and extending them to these more abstract settings, we suddenly unlock new levels of understanding. We make connections we couldn't see before.
It's like upgrading our mathematical glasses to see the universe with more clarity.
Exactly. And secondly, it's crucial to remember that mathematics is about making those connections. It's not just about isolated fields, but about seeing the bigger picture, the interconnectedness of it all.
It's like that feeling when you're finally able to step back and see the entire tapestry instead of just individual threads. It's quite beautiful, actually.
It really is.
Well, on that note, I think it's time to wrap up this mathematical deep dive. But before we go, I want to leave our listeners with something to ponder, a question that lingers. Given how successfully this paper uses these almost Hermitian structures to explore those moduli spaces of non-Abelian monopoles, could we apply similar techniques to other types of moduli spaces? Could we unlock even more secrets in, say, string theory or other areas of theoretical physics? What do you think?
Now, that is a fantastic question, and honestly, I don't have a definitive answer. But that's the beauty of it all, isn't it? This paper has opened up a whole new avenue of exploration, and I, for one, am incredibly excited to see where mathematicians and physicists take these ideas next. Who knows what incredible connections and discoveries await us?
It's an exciting time to be a math enthusiast, that's for sure. A huge thank you, as always, for joining us on this thrilling deep dive into the world of advanced mathematics.
My pleasure.
And to all our listeners out there, until next time, keep those mathematical minds engaged. Keep asking those big questions, and never stop exploring the fascinating world of numbers, shapes, and the intricate beauty of mathematics. All right, let's dive right in, shall we? Non-Abelian monopoles and symplectic form manifolds. Sounds a bit intimidating, maybe, but it's fascinating stuff. We're going deep into almost Hermitian structures on moduli spaces.
And it's groundbreaking stuff, really. This isn't just some obscure corner of math. This is about uncovering the fundamental geometric structures in these spaces, the implications for gauge theory, even theoretical physics. Well, they're huge.
Right. Before we get ahead of ourselves, let's set the stage for our listeners. We're dealing with moduli spaces. Think of it like each point in this space represents a different solution to a set of equations.
Exactly.
And specifically, we're looking at those spaces for non-Abelian monopoles. And these are, well, they're special solutions in gauge theory. Think of them like configurations of fields with unique properties.
Yeah, it's like taking something familiar, like a complex structure, from complex numbers, and giving it a twist, viewing these moduli spaces through a warped lens almost.
It's like we're charting a new world. We're exploring uncharted territory, trying to understand its shape, its peaks and valleys, how everything connects.
Exactly.
And that's where the topology and the geometry, those are the keys to understanding these moduli spaces.
Precisely. And the paper itself, it jumps right in. Page 4, they introduce this concept of a circle action. Imagine it like rotating the entire space. But the structure stays the same. And this is where it gets interesting. Because Frankel's theorem, It links special points in this space, critical points of something called the Hamiltonian function,
Right.
to fixed points of this action, the points that don't move during the rotation.
Okay, so we're like, what, putting down markers in this space, like landmarks?
Exactly, pinpointing key locations. And then they go even further using something called the virtual Morse-Bott index.
Okay, now that sounds a bit intimidating. What is that exactly? And why should we care?
So think of it as a way to classify these points. Are they peaks? Are they valleys? Something in between. This classification, it's essential because it affects how things move, how things flow on the moduli space.
Ah, okay, so it's all about understanding the shape of our mathematical landscape.
Exactly. And there's this key finding. These indices, they're always positive for the specific structures being studied. That means these critical points, they can't be local minima. And that has huge implications for how we understand the flow, the dynamics on this moduli space.
So these critical points, we're starting to get a grasp on them. But zoom out for a second. Why does this matter? Why are mathematicians so fascinated by these almost Hermitian structures? What's the big deal?
Right, so one of the key things here is understanding the topology of symplectic four manifolds. These spaces, they've got this special geometric structure and they pop up everywhere in math and physics. And this paper, they bring in this powerful tool to study them, the Bogomolov-Miyakoyau inequality.
Oh, okay, yeah, that rings a bell. It's always seemed a bit mysterious, though. Can you break that down for us?
Sure, it's like imagine a fundamental rule, a mathematical equation that governs these properties of a space, geometric and topological properties. It's about how these different aspects, they have to balance each other out. And what they're doing in this research is they're checking if this famous inequality, does it actually hold true for these specific moduli spaces, which are examples of symplectic four manifolds.
So we're taking these moduli spaces and we're putting them to the test, like running them through this mathematical obstacle course.
Yeah, exactly. And it goes even further. On pages 13 and 19, they bring in another player, Hitchin's Hamiltonian function.
Another Hamiltonian. But we just talked about, didn't we already cover the Hamiltonian and its critical points?
You're right, we did. But this one, it's specifically tied to the almost Hermitian structure. Think of it as an energy landscape, right, governing these monopoles.
Yeah.
Peaks, valleys, just like a real landscape. And those critical points, those are the flat spots, crucial to understanding the whole structure.
So we're mapping out the energy of the landscape, looking for where things stabilize. How does that help us understand the entire moduli space, though?
Well, these critical points, they're not just isolated. There are these things called flows, continuous paths connecting them. Think of it like tracing the behavior of the monopoles as we tweak things, and how these flows behave, converge, diverge. It all depends on the nature of the critical points.
So the critical points, they're like what? Attractors?
Yeah.
Or repellers shaping the entire flow?
Exactly. And here's where it gets really interesting. They introduce conjecture one. It's this bold idea, suggests a specific relationship between certain topological invariants of the moduli space. If they could prove it, it would have huge implications.
It's like proposing a new law of physics almost, but for these moduli spaces.
Right. But they're also honest about the limitations. They say, hey, our current methods, they might not be enough to prove this thing completely, specifically when dealing with spaces that have this property B plus Velc.
So a potential roadblock.
Yeah, and to illustrate it, they bring up these ruled complex surfaces. Fascinating things. They can actually violate the inequality in the conjecture.
Throwing a wrench in the works.
Exactly. But that's how we make progress, right? So they look at an alternative approach, Taub's perturbation technique, introduced back on page 4. It's a clever way to analyze Seiberg-Witten invariants.
Okay, hold on. Got to pause you there. Crash course on Seiberg-Witten invariants. What are they?
Sure. Think of them as like fingerprints, numerical fingerprints of the solutions to certain equations in gauge theory. Notoriously hard to compute directly, but this Taub's technique, it makes them manageable.
Like a shortcut.
Exactly.
Exactly.
You're changing the rules a bit to make the solutions easier to find, but they still tell you something important about the original problem.
A clever workaround.
Rare. And then they connect this to the work of Simon Donaldson.
Oh, Donaldson. The
Yeah.
symplectic geometry guy.
The one and only. They draw this parallel between his work on symplectic submanifolds and their own research.
So we're zooming in on specific regions of this moduli space.
Exactly. And Donaldson's work gives us the tools to see how these submanifolds fit within the bigger picture.
Building a more and more detailed map as we go.
Precisely. And that leads us to Theorem 12. That's a big one. A major simplification.
Always a fan of simplification.
Right. So remember how we talked about relating those critical points to these simpler Seiberg-Witten monopoles?
Yeah.
Theorem 12 says all critical points with a non-zero section, they can be completely understood in terms of these simpler objects.
It's like finding the Rosetta Stone for this area of math.
Exactly. We can now use everything we know about Seiberg-Witten monopoles to understand Hitchin's Hamiltonian, the critical points, the whole shebang.
Like a secret passage into this incredibly complex world. So it's like we've cracked the code. We can now understand this complex system by breaking it down into its simpler parts.
Exactly. But it doesn't stop there. They push even further with this. The second half of the paper, it gets pretty intense, lots of technical details. On page 78, they bring up these Taub's differential inequalities.
Differential inequalities. Okay, we're in the weeds now. Give me the gist. What are they and why should we care?
So basically, they're like these constraints, right? They limit how solutions to certain equations can behave. Remember the flows we talked about?
Right, on the Moduli Space.
Yeah, these inequalities, they're like boundaries for those flows. They can't just go anywhere.
So we're putting up fences on our landscape.
Precisely. And those fences, they're not random. They come from the geometry, the topology of the whole Moduli space. Then on page 117, they use another tool, the maximum principle.
Maximum principle. That rings a bell, vaguely. Doesn't that have to do with, like, finding the highest point on a curve?
Sort of.
Yeah.
In this context, it's about figuring out where a function reaches its maximum value, but within a specific region. Imagine a mountain range. This principle tells you, hey, the highest peak, it has to be on the edge, not somewhere in the middle.
Ah, okay. So they're using this to find those extreme points, those maximums, in our moduli space within those flow patterns.
Exactly. And using all of this, the Taub's inequalities, the maximum principle, they really get into the nitty-gritty of these monopole equations.
Dissecting them under a mathematical microscope.
Right. And then they introduce this concept, a blow-up.
Blow up? Sounds dramatic. What's blowing up?
It's from algebraic geometry. Imagine a surface, but it's got a sharp point, a singularity. A blow-up is a way to smooth that out, replace that point with a whole line.
So ironing out the wrinkles in our mathematical fabric.
Exactly. It helps us understand how things behave near those tricky singularities.
Like we need special glasses to see them clearly.
Perfect analogy. Then there's the S1 equivariant index of the deformation operator. Bit of a mouthful, I know.
Yeah, that's a lot. Break that down for me.
Okay, so the deformation operator, it basically tells us how solutions change when we tweak the problem a little bit.
Measuring their sensitivity to change.
Yeah. S1 equivariant means it works with those rotations we talked about, the circle action. And the index, it's like a counter, tells us roughly how many solutions there are given certain parameters.
So it's not just about finding one solution, but understanding all the possibilities.
You got it. They analyze this index to learn even more about the moduli space, those critical points.
We're getting a much clearer picture of this mathematical world.
Right. And this leads to a really cool result. They generalize a criterion from Donaldson about symplectic submanifolds.
Donaldson again. Seems like his work is the foundation for all of this.
He was a genius. What they do here is amazing, though. They take his idea, which was very specific, and make it way more abstract. Now it works with these things called Hilbert spaces.
So they took a specialized tool and made it universally applicable.
Exactly. And this allows them to use his ideas in their own research on the moduli space of non-Abelian monopoles. They then bring in these concepts, reducible, split, and central stabilizer unitary connections.
Okay, I'm going to need some help with those terms. What are those in simple terms?
Think of them like building blocks, different types of connections that make up the moduli space. Each one's got its own properties, symmetries. By understanding them, we understand the bigger picture better.
We're breaking down a complex machine into its parts.
Yes. And they extend this to spin-C structures, too, which bring in this idea of spin, something really fundamental in quantum mechanics.
Oh, so we're connecting to the quantum world now.
Right, it's all connected. Then there's the Morgan-Rocha condition, which is a rule, basically. It tells us which solutions are important, which ones fit into this framework.
Narrowing down the possibilities.
Right, and all of this, it leads to a very deep analysis of Hitchin's Hamiltonian function. They define its critical points precisely.
Mapping out that energy landscape we talked about.
Yes. And they prove a crucial theorem, Theorem 12, that characterizes these points. Remember how we said they can be related to those simpler Seiberg-Witten monopoles?
Yeah, like a translation guide.
Well, Theorem 12 says all the critical points with a non-zero section, they all come from these simpler objects.
So those Seiberg-Witten monopoles, they're even more fundamental than we thought.
Exactly. We can use everything we know about them to understand this whole structure. And to do that, they compute something called the virtual Morse-Bott index for Hitchin's Hamiltonian.
That index again, it's
Yeah.
everywhere. So we're getting into actual calculations now, not just concepts.
Yeah. And to do this, they use the Atiyah-Singer index theorem.
Mhm.
It's a heavy hitter, connects analysis and topology in a deep way.
Using the very fabric of mathematics to solve this.
Beautiful way to put it. Through these calculations, they show how this index, it can be expressed in terms of more basic topological things.
Connecting all these abstract ideas in a concrete way.
Exactly. And they've given us a way to actually calculate this, understand Hitchin's Hamiltonian, and the Moduli Space itself.
Like a map leading us to hidden mathematical treasure.
I like that. But of course, like any good exploration, they don't just stop there. They end by pointing towards the future. Can we use these techniques for other types of moduli spaces? What other areas of math and physics can benefit from this?
So many possibilities. They've opened up a whole new world for us to explore.
That's the beauty of it, isn't it? It's not just about answers, it's about the questions, the endless pursuit of knowledge.
Absolutely. Well, this has been an amazing journey. We've covered so much ground, from those non-abelian monopoles to the geometry of moduli spaces and beyond.
It's been a pleasure, really.
To our listeners, keep exploring, keep those questions coming, and we'll see you next time. All right, everybody, let's dive into something really fascinating today. We're going deep into almost Hermitian structures.
And their connections to a pretty big mathematical conjecture, in fact.
That's right. We're looking at a paper called Almost Hermitian Structures on Moduli Spaces of Non-Abelian Monopoles and Applications to the Topology of Symplectic for Manifolds.
Quite a mouthful.
It is. So you ready to unpack some serious math?
Absolutely. This paper is a wild ride. It really jumps right into some deep stuff.
Right.
We're talking about the geometry of these moduli spaces and what they can tell us about four-dimensional spaces.
And at the heart of all this is something called Conjecture 1. Could you give us a quick rundown of what that's all about?
Sure. Conjecture 1, it suggests a really deep link. It connects these special properties we call almost Hermitian structures on these moduli spaces to something called the Bogomolov-Miyaoka-Yau inequality.
Okay, and the Bogomolov-Miyaoka-Yau inequality, just as a reminder for our listeners, it's all about setting boundaries on curvature right, specifically for certain types of complex surfaces.
Precisely. And this inequality, it's like a cornerstone in complex geometry.
So proving this conjecture, that would be like finding a secret passage, wouldn't it? Connecting all these different parts of mathematics.
Absolutely. It would be huge, solidifying a connection that we've suspected but haven't quite nailed down.
Now, the paper starts off strong, talking about almost Hermitian structures, especially in 4 dimensions. What makes those so interesting? What's so special about 4 dimensions when it comes to this?
You see, in 4 dimensions, these structures become incredibly powerful. They're like a specialized lens helping us examine these spaces, understand their topology. They provide a framework for studying things like symplectic forms, which are crucial for understanding area and how things move in these spaces.
So almost Hermitian structures, they're like a key to unlocking the secrets of these 4-dimensional spaces.
That's a great way to put it. And what's particularly fascinating here is how the authors use these structures to understand things called non-abelian monopoles.
Okay, now, non-abelian monopoles. That sounds intense. Could you break that down for us a little bit? What are we dealing with here?
Imagine them as solutions to some pretty complicated math equations. Equations that come from gauge theory, to be precise. And the behavior of these monopolies, it's all dictated by the geometry of the 4-dimensional space they live in. It's a bit like, imagine trying to predict the movement of particles in a magnetic field.
Except our magnetic field is this strange 4-dimensional world with its own set of rules.
Exactly.
And just to add another layer of complexity, they bring in moduli spaces. For those who haven't encountered those before, how would you explain their role? Because I know moduli spaces can be a bit of a head-scratcher.
Think of a moduli space as a sort of catalog or a map. It lists out all the different ways these non-abelian monopolies can arrange themselves within our 4-dimensional space. Instead of tracking every single particle, we're looking at the big picture, all the possibilities.
So by studying the moduli space, its properties, its geometry, we can learn something about the monopoles themselves and the space they exist in.
Exactly, and that's where the connection back to Conjecture 1 comes in. You see, the authors, they suggest that if this moduli space has certain almost Hermitian structures, then boom! We can prove the Bogomolov-Miyaoka-Yau inequality holds for the underlying four-manifold.
So the geometry of this catalog of monopoles is telling us something fundamental about the space itself.
Precisely. And to simplify things a bit, the paper focuses on the case where the four-manifold is in collar manifold.
So a specific type of four-manifold, one with a particular, almost Hermitian structure.
Right, and in this collar case, something really interesting happens. The moduli spaces, they kind of inherit this collar structure, at least in the well-behaved regions.
So the moduli space gets a little piece of the collar blueprint from the four-manifold, making it a bit easier to work with.
Exactly. And this inherited structure isn't just a coincidence, it's a crucial part of their analysis.
The paper mentions that this inherited collar structure leads to what's called a circle action on the moduli space. Now, I'll admit my group theory is a bit rusty. Could you give us a refresher on what a circle action entails?
Of course. Imagine you have a spinning top. Each point on that top is moving in a circle, but the top itself, its overall shape, stays the same. A circle action on the moduli space is similar. It's like a continuous rotation or symmetry that preserves the space's structure.
And this circle action, it's not just there for visual aid, right? The authors use it to define something called Hitchin's Hamiltonian function on the moduli space.
That's right. It has a very specific purpose. Think of Hitchin's Hamiltonian as a way to assign an energy level to each point in the moduli space. This function is tied to the circle action, and its critical points, where the energy is at a standstill, they correspond to specific configurations of our non-abelian monopoles.
It's like creating a topographic map of the moduli space, showing us the peaks and valleys of this energy landscape.
A great analogy. And what the authors do next is brilliant. They link these critical points to another type of monopole called a Seiberg-Witten monopole. And these Seiberg-Witten monopoles, they're essential in gauge theory.
Oh, okay, so we're going deeper into the theoretical physics here. What's so special about these Seiberg-Witten monopoles? Why bring them into the picture?
They're crucial for understanding the topology of four manifolds. They're well studied, and by linking them to the critical points of Hitchin's Hamiltonian, the authors create this bridge, allowing them to transfer knowledge between these two areas.
So it's like finding a secret passage between what seemed like separate areas of study, and who knows what we might discover with this new connection.
Exactly. And the paper, it goes even further. It states that something called the virtual Morse-Bott index of these critical points, it's always positive. This little detail, based on something called Frankel's theorem, it's going to be key in their strategy for tackling conjecture 1.
So we've got these monopoles guiding us, moduli spaces as our maps, and a Hamiltonian function as our energy compass. It really does feel like a mathematical adventure, doesn't it?
It does, doesn't it? And like any good adventure, there are clues to be found along the way. And the authors, they point to a big one, Wu's theorem.
Okay, Wu's theorem. Refresh our memory on that one. What role does it play in their exploration?
Wu's theorem, it gives us a link, a really important link between these almost complex structures and a specific cohomology class, we'll call it K. Think of this class as a way to encapsulate information about how twisted this almost complex structure is.
So it's like Wu's theorem is a translator, helping us understand almost complex structures in a different language, the language of cohomology.
Precisely. It provides the dictionary we need to decode the geometric secrets hidden within these classes. And one relation in particular, K sub 2 sub x sub top x sub, where C sub 1 sub x represents the first Chern class of our four manifold, this becomes a cornerstone in their analysis.
Now, they do point out a bit of a limitation in their approach, specifically when dealing with four manifolds with bead sub plus sub xx equals 1.
Yeah.
What's the snag there?
That's an important caveat, you're right. Their methods, they hit a bit of a roadblock in this specific case. It's because certain four manifolds, like ruled surfaces with genus 2 or higher, they don't quite fit with the Bogomolov-Miyaoka-Yau inequality, which is, of course, central to conjecture 1.
Ah, so it's like encountering a detour on this mathematical journey. These particular surfaces, they throw a wrench in the works.
You could say that. However, it's not a complete dead end. It just means they'll need different tools to handle those specific cases.
Yeah.
Their approach is still very powerful for a wide range of symplectic four manifolds.
So not a dead end, just a fork in the road.
Exactly. And think about it, even proving conjecture 1 for a subset of these manifolds, that would still be a huge achievement in mathematics.
Oh, absolute groundbreaking. It would significantly impact our understanding of these spaces.
It really would. And another point worth mentioning, If conjecture 1 turns out to be true, it would immediately tell us that the Bogomolov-Miyakovow inequality holds for a whole bunch of symplectic four manifolds.
The paper explicitly mentions that, right? It's
Yeah.
like getting double the mathematical bang for your buck.
Absolutely. I mean, the Bogomolov-Miyakovow inequality, it sets such a crucial limit on curvature that proving it for these four manifolds would be a major victory in itself.
So conjecture 1, if true, it has implications way beyond these moduli spaces and monopoles.
It highlights just how interconnected these different mathematical concepts really are.
Now, there's one more piece of the puzzle I'd like to touch on before we move on. The paper mentions this congruence, EX plus CODO mod 4. Can you break that down for us? What's the story with that congruence?
Ah, yes, that congruence. It's a fundamental condition for a four-manifold to be almost complex. Essentially, it links the Euler characteristic, denoted by EX, to the signature of the manifold, stating that they have to satisfy this specific relationship for an almost complex structure to even exist.
It's like a compatibility check, making sure everything aligns before you can even begin to talk about almost complex structures.
Exactly. It acts as a gatekeeper, preventing us from combining incompatible structures. And this has an interesting consequence, by the way. You can't just take two almost complex four manifolds, stick them together, and expect to get another one. The connected sum, which is a way of gluing manifolds together, it disrupts this crucial congruence.
So you can't force it. The congruence is like a mathematical sign saying, sorry, no entry.
Precisely. It just goes to show the importance of these seemingly subtle conditions in mathematics. They're the rules that keep everything consistent.
All right, so we've laid out the groundwork, met the key players, and even encountered our first few mathematical hurdles.
It's been quite a journey already, and we're just getting started.
Exactly. Now we need to see how the authors actually start to piece this all together, how they take these concepts and build a case for conjecture 1.
And that is where things are going to get even more interesting.
Okay, so we've got all the ingredients, all the tools laid out. How do the authors even begin to build a proof for conjecture 1 with all of this? Where do they even start?
Well, they take a very structured approach. They break the proof down into smaller, more manageable pieces, kind of like, you wouldn't build a house starting with the roof.
Got to have that foundation.
Exactly. They start by focusing on showing that a very special type of connection exists. They call it a projectively anti-self-dual connection. And this connection, it lives on a complex line bundle over our four manifold.
Projectively anti-self-dual connection. Okay, that's a mouthful. You mind unpacking that a bit? Why is this connection so important?
Of course. It's all about the properties. This particular type of connection has characteristics that, under the right circumstances, lead directly to the Bogomolov-Miyakovow inequality. Remember, that's our ultimate goal here, connecting back to that inequality.
Right. It's like they're building a bridge, using this special connection to connect those two worlds. So how do they go about actually showing that this connection exists? They can't just pull it out of thin air.
No magic tricks here, just good old-fashioned math. They utilize what's called a gradient flow. Imagine you've got a drop of water on a curved surface. Naturally, that drop is going to flow downwards, following the path of least resistance, right?
Until it reaches a stable point, yeah.
That's our gradient flow. They essentially define a function, and this gradient flow, it's like gravity pulling them towards that special connection.
I see, but we talked before about that roadblock they hit when beep sup plus sup x equals 1. How does that affect their construction project?
That's where things get really clever. To get around this issue, they introduced something called a blown-up version of the four manifold.
Blown up? Now, I'm really intrigued. What does that even mean in this context?
So imagine you have this perfectly smooth surface. Now take a single point on that surface and replace it with a tiny little sphere. That's essentially what blowing up does. It adds a new feature to the manifold.
I see. So it's more of a topological adjustment than an actual blowing up. By doing this, they kind of sidestep that b sup plus sub x equals 1 issue.
Precisely. This little blow-up allows their gradient flow techniques to work their magic more effectively.
Like creating a detour around that mathematical roadblock.
Exactly.
Okay, so they've blown up the manifold. What's next?
Well, now the goal is to construct that special connection, the projectively anti-self-dual one, but this time on this modified, blown-up manifold.
So they've moved their construction site hoping for smoother sailing on this blown-up version.
That's one way to put it, and it turns out this little trick works wonders. They're able to establish very precise conditions that guarantee the existence of that special connection, but on this blown-up manifold.
So even though they added complexity with the blow-up, It ultimately gave them the tools they needed to move forward.
It's often like that in math. You have to embrace the abstract to make progress.
Now, I noticed they spent a fair amount of time on specific cases, ruled surfaces, complex surfaces with blowups. Why the focus on these particular examples, especially if they're aiming for a more general proof?
Those examples are their testing grounds. Think of it like testing a new recipe. You start with small batches, right? By working through these well-understood cases, they gain insights into how the gradient flow behaves.
It helps them refine the conditions needed for this special connection to work its magic.
Exact.
Okay, that makes sense. Now, another thing that kept popping up was the idea of perturbations. Could you shed some light on those? What role do they play?
So a perturbation is like a tiny nudge or a tweak you make to a system just to see how it reacts.
You're testing its limits, seeing how robust it is.
Precisely. And they're using a very particular type here, a Taub's perturbation. It's named after Clifford Taubes, a prominent mathematician who really pioneered this method.
So it's not just any old nudge, it's a very specific calculated nudge.
Mm-mm.
Why the Taubes perturbation in particular?
It's all about accuracy. The Taubes perturbation is designed specifically for the types of equations they're dealing with, the equations that govern these monopoles and their moduli spaces.
It allows them to make very precise estimates, which I imagine is crucial in this line of work.
Oh, absolutely. They're using this to get estimates for something called the coupled spinor, a key ingredient in their equations.
It's all about keeping things in check, making sure those estimates are tight.
Precisely. Without those estimates, their whole construction could become unstable.
It's delicate work, this mathematical architecture. Now, as we go further down the rabbit hole here, things start to get even more abstract. We're talking Hitchens Hamiltonian, circle actions, virtual Morse-Bott indices. How do these all tie into the bigger picture?
Think of them as essential tools. Each one helps us understand the geometry of that moduli space and how that gradient flow behaves.
Okay, so let's break it down. We've talked about Hitchens Hamiltonian, how it gives us this energy map of the moduli space.
Right, and remember those critical points on our map, the peaks and valleys? Those correspond to special arrangements of monopoles, arrangements that are fixed by the circle action.
Right, the circle actions, like rotations that preserve the structure of the moduli space.
Exactly, and that's where those virtual Morse-Bott indices come in. They tell us what's happening at those critical points. Are we at a maximum, a minimum, or something in between?
They add another layer of information to our map, helping us navigate this complex terrain.
Precisely. And by carefully studying these indices at those special fixed points, the authors can understand the dynamics of their gradient flow, which is crucial for showing that it actually leads them to that special connection they're looking for.
So they're using energy, symmetry, and a whole lot of ingenuity to steer their mathematical ship towards the solution.
You've got it. It's a beautiful interplay of different mathematical tools.
We've gone pretty deep into the machinery of their proof. Now the authors bring in the big guns. They start talking about the Atiyah-Singer index theorem. And I've always seen that as one of those elegant results in mathematics. How on earth do they apply that here?
It's true. The Atiyah-Singer index theorem is incredibly powerful, connecting so many different areas of math. In this case, they're using a version of it that's specifically designed for situations with a circle action, something called the S1 equivariant index.
Right, because we have that circle action on our moduli space.
Yeah.
So they're using this theorem to take that geometric information, that symmetry from the circle action, and translate it into a language that lets them analyze the moduli space itself.
Exactly. It's like a mathematical Rosetta Stone, helping them decipher the secrets hidden within that geometry.
Yeah.
And what they find is amazing.
Okay, I'm hooked. How does this index get us closer to that Bogomolov-Miotke-Yau inequality? It feels like we've been building this amazing bridge, but haven't quite crossed it.
We're almost there. It's all about connecting the dots. Remember those points in our moduli space that are fixed by the circle action? Those special configurations of monopoles?
Right, where the energy from Hitchens Hamiltonian is sort of at a standstill.
Right. Well, the authors, they make this brilliant connection between those fixed points and those Seiberg-Witten monopoles we talked about earlier.
Oh, okay. Things are starting to click now.
They calculate the virtual Morse-Bott index. Remember those signposts on our energy landscape at those specific fixed points? And guess what? They're able to directly relate those indices to the Seiberg-Witten invariants.
And those invariants are directly tied to the topology of the four-manifold. We're finally connecting back to the bigger picture.
Exactly. And there's a crucial observation here. Their calculations show that this virtual Morse-Bott index at those fixed points, it's always positive.
So those Seiberg-Witten configurations, they can never be points of minimal energy.
Precisely. They're always trying to roll downhill, never settling at the very bottom. And this seemingly small detail has huge implications. It creates this amazing link between the geometry of the moduli space, represented by those indices, and the topology of our four-manifold, represented by those Seiberg-Witten invariants.
It's like the index is the missing piece of the puzzle, connecting everything together.
Exactly. And they take it even further. They actually rewrite that virtual Morse-Bott index, expressing it in a way that highlights its connection to those invariants.
So they're rearranging the equation, so to speak, making that connection impossible to miss.
Exactly. It's like shining a spotlight on the key terms that link everything together. And they don't just do it one way. They present a few different ways to rewrite it, each offering a unique perspective.
So we get a complete 360-degree view of this index and its connection to the four manifolds topology.
Precisely. And with all this groundwork laid out, they finally circle back to that Bogomolov-Miyakoyao inequality.
The moment of truth. How do they finally bridge that gap?
They show that the virtual Morse-Bott index, when it's expressed using those carefully chosen topological invariants, can be directly related to the terms in the Bogomolov-Miyakoyao inequality itself. And through a clever analysis of this relationship, they aim to demonstrate that the positivity of the index, remember, always positive at those special points, actually implies that the inequality itself holds true.
So it all hinges on that index. It connects the geometry of the moduli space to the topology of the four manifold, which then has to obey the Bogomolov-Miyakoyao inequality. It's an incredible chain of logic.
And it's a testament to the power of abstract reasoning. Even though they don't completely prove conjecture 1 in its most general form, their work offers incredibly strong evidence for a wide range of cases.
This paper, it's like a beacon, lighting up a new path in mathematics, leading to some incredible discoveries.
And showcasing the beauty of this field.
Absolutely. Well, on that note, I think we've reached the end of our deep dive. It's been quite a journey, exploring the intricate world of almost Hermitian structures, moduli spaces, and monopoles.
A wild ride through some really high-level math.
But hopefully, it leaves you, our listeners, with a sense of awe for the power and elegance of mathematics. Until next time, keep those brains buzzing.